This video is part of an initiative of the Geoenvironmental Engineering Technical Committee of the ASCE Geo-Institute to create a series research to practice videos. These are intended to be brief, straight to the point videos that summarize research findings published in scientific journals that can be of value to practicing engineers. My name is Dimitrios Zekkos, and I'm an associate professor at the University of California at Berkeley. Today, I'll be talking to you about dynamic compaction on municipal solid waste sites. This is work that we've done with Mohammed Kabalan and Michael Flanagan, and was published in the ASCE Journal of Geotechnical and Geoenvironmental Engineering Journal in the address shown below. Very briefly on the methodology, this is a case histories database and synthesis of 56 test sites at 33 municipal solid waste landfills or waste dumps where dynamic compaction has been conducted. There is a table in the paper that has detailed information for each of those test locations, but very briefly, 19 of the sites are in the United States, 7 in the UK, and the rest are distributed around the world. Dynamic compaction is a relatively popular ground improvement technique on solid waste. It has the most extensive record compared to other ground improvement techniques. The technique is based on dropping a weight W from certain height repeatedly, causing a crater into the ground and densifying the material below. The figure on the lower right shows from the case histories that we have on solid waste landfills the ranges of height drops and weight of pounders. You can see that the weight of pounders is 10 to 20 tons or megagrams, and the height from which this tamper or pounder is dropped is 10 to 30 meters. Probably the main reason for doing dynamic compaction is to improve the ground to some depth, and so the depth of improvement is really, really important. In engineering practice, we use the relationship shown here that essentially relates the depth of improvement to the energy input, W times H, to the square root, multiplied by N, which is a coefficient related to the site conditions. And in the figure on the left, you can see the drop energy on the x-axis and the depth of improvement in the y-axis. And overall, the data drops along falls at a range of n values of 0.4 plus or minus 0.05 for the most part. This results in depth of improvements in solid waste that are shallower, smaller depths than the depths of improvement that we've seen in cohesionless soils, which have generally values of n of 0.6, 0.65. So that's important to consider. The applied energy is the total energy applied during the technique, and it's essentially the product of the weight times H, times the number of tamper drops, times the number of passes, times the gravitational acceleration, divided by the total area that is improved. And the lower figure shows the frequency distribution of the level of applied energy, and you can see that most commonly applied energies of 200 to 400 metric tons times meters times divided by meter square have been used, but higher have been used also. Overall, during the technique, significant settlement takes place because there are craters that are forming, and we can calculate that settlement as a function as a vertical strain. And we can see that this vertical strain is a function of the applied energy applied. So if you apply more energy, you will get more strain. But what I would like to communicate for today is that you can see that vertical strains up to 30% are feasible from a perspective of dynamic compaction. Now, when we do dynamic compaction, we see a significant increase in stiffness. There is an increase by a factor of 3 to 25, 24, and compared to the same material in an improved state. And that's a significant increase associated with a denser waste matrix. However, for those that are working on solid waste locations, know that the most critical consideration is not the response to a load, but the secondary compression settlements, the settlements that are associated long-term, that are typically associated with biodegradation of the solid waste. And so equations like these are used where the settlement is equal to the thickness of the solid waste times a modified secondary compression coefficient times the delta log of T. And that secondary compression coefficient appears to be taking values of 0.01 to 0.05 for dynamic compaction improved sites, which is a lower value than sites that haven't been improved, that can have significantly higher values than those. So it seems that although dynamic compaction is a technique that, from a mechanics perspective improves, densifies the material, that higher density and more stable structure of the solid waste has an overall positive impact on reducing the long-term settlements also. Finally, vibration is caused by dynamic compaction, by the drop of the tamper on the ground, is an important consideration. And what I would like to point out, as shown in this figure, is that overall, the solid waste sites, shown here with red squares, triangles, and blue circles, are lower, have lower peak particle velocities for the same energy input than the crosses, which are soil sites. So vibrations are attenuated faster at solid waste sites than in organic soils. And so that's important to consider. That's a good news. This is very briefly the findings of this work that was that can be found in more detail in the cited paper. And I would like to point out that additional research to practice videos can be found on the Geoenvironmental Engineering Technical Committee website at the address shown. Thank you very much.